Okay, good morning, everyone. Welcome to our tutorial. It is Wednesday, the 21st of February, 7:40. I've had a question about absolute and relative uncertainties. We have two boxes. As physicists, we try to quantify the world. We want to know not just why or when, but how much. We like to know exactly how much. So we go and we try to measure the world. We have the two boxes. We're going to try and measure the two boxes. When we go to measure the two boxes, we are applying this human scale. We made this up. This human scale is made up by us. We're applying a human scale to a real world thing. And so there's always going to be uncertainty. There's limitations to how well I can read the human scale. There will always be uncertainty. As I go to use this human scale for length, I'm going to be starting with absolute uncertainty. So we'll go have a look at that one. So at the moment, I'm reading 48.5 centimeters. That's my reading on it, the length of the box. What's the uncertainty? When I look at the actual scales on my ruler, the smallest individual scale is 0.5 centimeter. So I guess my uncertainty is going to be the smallest, it's going to be plus or minus half of the smallest interval, which is always going to be plus or minus half of that 0.5 centimeter. So this is our absolute uncertainty. This box over here is the twin of that box over there. And so the length of that box, when I go and measure that box, we'll just say that it's the same. When I do the uncertainty for absolute uncertainty, then it's going to be in the same unit. So 48.5 plus or minus 0.25 centimeters. That is a convention. You don't have to do that. You could, if you wanted to, you could say, yes. So yes, you could say 48.5 centimeters plus or minus 2.5 millimeters. Yes, you could. That's not what we do in convention. In convention, we represent it like this. Okay. All right. Now we want to add these or put these two boxes next to each other. How long would they be? Well, we could just put them there and measure it. And hey, presto, we've got the answer. But say we don't have the boxes with us. And so we want to predict how long the boxes will be when we put them together. Okay. Where would that happen in the real world? Well, you know, you got in that team over there is manufacturing the box. This team over here is manufacturing the box. And you know that these two boxes have got to fill a gap over there. So you don't want to wait until you've built them to see if it works. So you make a prediction early on. You say, well, we're going to add them together. These are our tolerances. Add them together. For adding or addition of uncertainty, we add the raw values of the absolute uncertainty. So we add them together, 48.5 and 48.5. At 97? Come on. I don't know. 90. Is it 98? Thank you. I'll be chopping that bit out. That's 97. I'll be chopping that bit out. Okay. So it's going to be 97. Okay, thank you. So these two together, 97 centimeters plus or minus that plus that. Okay, so 0.5 centimeters. All right, so that's if we're adding or subtracting. If we're adding or subtracting, then we sum the absolute uncertainties. So let's look at it. Yeah, either way. So let's look at this. When we look at this, we could be asking this question. So in terms of absolute uncertainty, we could be asking the question, well, what's the worst case scenario here? What's the smallest it could possibly be? 48.5 minus 0.25. 48.5 minus 0.25. (96.5 centimeters is the smallest it could be. 97 minus 0.5. Okay. What's the biggest that they could possibly be? We add them. So 48.5 plus 0.25. Yeah, thank you very much. Okay, so that's the biggest they could possibly be. Let's look at subtracting absolute uncertainty. So subtracting absolute uncertainty. So now, in this situation, we imagine we've got two boxes, box A and box B. We're going to use them to fill a hole. But the problem is we want to know how what's left, or rather, let's look at it this way. Box A is being taken out of a hole. Box B is going to be put into the hole. What's the gap? Because box B is smaller than box A. What's the gap going to be? So we're going to need to do a subtraction. G'day, mate. Good to see you. Okay, so we're going to look at that. We have to measure box B. So we have box B, 36.5 plus or minus 0.25. So we go to subtract these values. Okay, so what's that going to be? That's going to be, is that going to be 12? What's that? Okay, equals 12.0 centimeters. And then we sum, even though this is a subtraction, we sum the absolute uncertainties. Okay, so when we look at that, we now can say that the two boxes, if you take A out of the hole, A was in the hole, A was good. We liked A. A was suiting our purposes as well. Take A out of the hole, put B into the hole. What's the gap? We've got 12 plus or minus 0.5 centimeters, okay? Which means it could be anything from 11.5 up to, it could be 12.5, could be that hole. So what's the worst? What are the extreme examples? Okay. So the biggest the hole could be is if this guy here was 48. If this guy here was 48.75, subtract 36.25. So I've added on the absolute uncertainty here. I've subtracted it over there. That would give us the biggest possible hole that it could be. And what would that give us? So that would give us 12.5. All right. The smallest hole that it could possibly be would be 2.5 subtract 7.5. And that would give us, if you look at that, that would give us 11.5. Okay, so for absolute uncertainties, plus or minusing quantities which are absolute uncertainties, you always sum the absolute uncertainties. Multiplying them. Okay, so we want to find the area of A. Okay, so multiplying them out, the area, we're going to have area equals length times breadth equals 48.5 multiplied by 13 plus, 13.0. Okay, so we've got that value there. But what is the uncertainty of that final area? When we are multiplying or dividing uncertainty, we always go for the relative uncertainty. We have to find that. So we're going to say that if this is the length times the height, our length is equal to 48.5 centimeters plus or minus that as a percentage of 48.5. So we get out our calculators, 0.25 times 100 divided by 48.5. So it's plus or minus 0.51. I would actually say 0.52%. Okay, so we've got that there. Then we say the height is equal to 13.0 centimeters plus or minus that as a percent of 13. 0.25 times 100 divided by 13, 1.92. Now they've got exactly the same absolute uncertainties, but straight away we notice because this is a smaller quantity, the absolute uncertainty is much more significant in a relative term. Okay, so that's worthy of knowledge. Right? That's worthy of noting. Okay, so when we look at that, we add these two together, 0.52 plus 1.92. And so we have a relative uncertainty of 2.44%. We want to find the absolute uncertainty of this. We ask ourselves the question, what is 2.44% of that? So we go 2.44 divided by 100 to transform percent into a decimal, multiply that by 630.5. And we end up with Did you? Okay.
I screwed up with percentages. Transferring it is not 4%. Right?
Okay.
But I got the process right. So
all right, good. So there's the process. You're getting that idea. If we raise a quantity to a power, so for example, if we're trying to find, if we raise a quantity to a power, we want to find the radius of a circle. Oh, we've got the radius. We want to find the area of the circle. Okay, pi r squared. So we've got that radius might be 4 centimeters plus or minus 0.5, which is the same as 4 centimeters. That's centimeters plus or minus 12.5%. So we're going to raise this. We'll get the area equals pi r squared, and then the relative uncertainty will be if we have this raised to a power. So our quantity is raised to a power, q to the power of n, then relative uncertainty equals when you combine them, it's the percent uncertainty multiplied by n. So in this case, when we get the area of that pi r squared, 50.3 square centimeters, then we're going to see that this is plus or minus 2 multiplied by that, plus or minus 25%.
So it's not squared. It's
yeah. Now, that's if you raise it to the power, you multiply it by that index, right? But it kind of makes sense because what actually is this? Yes. Yes. So you're absolutely correct. So you said then if it was cubed, we're going for volume, so 4/3 pi r cubed, in that situation, it wouldn't just be r to the raised to the power of 3. It would be r times r times r. And if we multiply, we add the relative uncertainty. So it makes sense. If you multiply itself by itself 3 times, you add the relative uncertainty 3 times. If you multiply by itself 2 times, you add the relative uncertainty twice. So that's absolute and relative uncertainty in a nutshell. Is that cool? Yeah. All right, cool.